Welcome to OP's Math e-Pathshala.
So, in the last lecture, I have ended up with this result, which says that that we be a finite dimensional vector space, then there exists a finite set of vectors v1, v2, vn, which are linearly independent. That is the first one property it has, and secondly, the vectors will span the whole space V. So the linear span of these vectors is V. So for a given finite dimensional vector space, you can always have a finite set of vectors v1, v2, vn, which are linearly independent and whose span is V. So this result follows from our discussion that we have already have in the previous lecture. Now I would like to define the linear independence and linear dependence for any subset. I have already talked about linear dependence and linear independence for a finite set of vectors, and now I am going to define it for any subset of a vector space V. So what is the definition? The definition looks like that let V be a vector space and A be a subset of V. A be any subset of V. Then S is said to be, then the subset is said to be linearly dependent. The subset is said to be linearly dependent if there exists a finite set of vectors, finite number of distinct vectors, suppose v1, v2, vn, in the set S, and you will also have finitely many scalars. That is, here, since we are getting n number of vectors, so we shall get n number of scalars. So scalars alpha 1, alpha 2, alpha n. And these scalars are not all 0. Not all are 0. Such that what happens? Such that the linear combination of these vectors with respect to these scalars, it will be the null vector theta. Okay, so the definition says that if we consider any subset of V, then this subset is defined to be linearly dependent if there exists a finite number of distinct vectors v1, v2, vn in the set S, and also n number of scalars alpha 1, alpha 2, alpha n, where these scalars are not all 0, such that the linear combinations with respect to these vectors and with respect to this scalar alpha 1, alpha 2, alpha 1 v1 plus alpha 2 v2 plus alpha n vn is going to be the null vector theta. Is null vector of the vector space V. So any subset can be defined to be linearly dependent if you can search out a number of vectors and a number of scalars, not all 0, so that their linear combination is 3. Okay. Note that any subset of a vector space, that contains the null vector is eventually linearly dependent. Please note that any subset of a vector space that contains the null vector must be linearly independent. Linearly dependent. Must be linearly dependent. Why it is true? Because you can always have this theta, the null vector, and since in the field F you have the unity. So because one dot theta equal to theta. So this is the vector and this is the scalar. So one dot theta is going to be theta. So for this reason, you can always say that any subset that includes the null vector will be linearly dependent. Okay. And reversely saying that so a subset S of V, so a subset S of V is said to be linearly independent if it is not linearly dependent. So it's said to be linearly independent if it is not linearly dependent. Yeah. Yeah. Okay. That is, what does it mean? That is any finite number of vectors in the set S is linearly independent. So just have a look at the definition minutely, that what does it mean by a subset is to be a linearly independent. That is, a subset is said to be linearly independent. If it is not linearly dependent, that means every finite set of vectors taken from the set S is linearly independent. That is for any finite set of vectors chosen from S must be linearly independent. Okay, independent. Okay. So it should be noted that the null set, if we consider the null set, that is which contains nothing. So if we consider the null set in a vector space, then that must be linearly independent. That must be linearly independent because due to the definition of linearly dependence, you can have that linearly dependent sets must be non-empty, because whenever you are talking about linearly that not linearly dependent, then you must have some vectors. So you can have some you can search out some vectors which are not linearly independent. So for this reason, the empty set must be linearly independent, because in linearly dependent sets there exists at least one vector. So that null set phi is linearly independent. Okay.
So note that the null set phi is linearly independent set. And okay, also note that any superset of a linearly dependent set in a vector space, any superset, any superset uh, of a linearly dependent set is also linearly dependent, is also linearly dependent, since uh, the same set of vectors will work for the superset. Suppose you consider a linearly independent set S, and S is a subset of, suppose, S dashed, that is S dashed is a superset of S. Now if S is linearly dependent, then you will find uh, some vectors, some distinct vectors Vn and in S, and you will find out n many scalars, not all 0, such that alpha 1 v1, alpha 2, alpha n vn equals to theta. Now since S is a subset of S dash, so these vectors v1, v2, vn are also vectors of S dash, and from this you can say that S dash is also linearly dependent. So this is very easy. Okay. And as a consequence of this observation, uh, we can show that any subset of a linearly independent set must be linearly independent. That is the converse of this. That is the uh, that is with respect to this observation. You can also deduce that any subset for linearly independent set, you need to consider subsets. So any subset of a linearly independent set must be linearly independent. Yeah. So this is true. So for linear dependence, any superset of a linearly dependent set is linearly dependent, and for linear independence, any subset of a linearly independent set is linearly independent. Okay. So keeping in mind these definitions, you can define an important observation, an important concept. What is the concept? As we have already exhibited some examples of linearly independent sets. Suppose whenever we are considering the field F and their n times Cartesian product Fn. So this vector space has a set of vectors like u1 is 1 0 0 0, e2 is 0 1 0 0 0, and so on. En is 0 0 0 1 0 1. Yeah. So this indexing is due to the place of 1 where it lives. Okay. So these vectors will form a linearly independent set of vectors. These are linearly independent. Okay. So these are linearly independent. Yeah. And also for any vector x in Fn, so it can be expressed as x will be some alpha 1 e1, alpha 2 e2, and alpha n en, where x is the coordinate, x is the point whose coordinates are alpha 1, alpha 2, alpha n. So this way of representation is unique, since these are linearly independent. Okay. So this set of vectors will be named as a basis of the vector space Fn. And in general, so let us consider a vector space. Let V be a vector space. So a set of vectors S, so a subset S of vectors in a vector space V is said to form a basis of the vector space V if the two conditions will be satisfied by the subset S. The first condition is S is linearly independent. Yeah. And the second condition is this set of vectors, so this will spans the vector space V. That is, the linear span of this vector, this subset is V. So if these two conditions are being satisfied by this subset S of vectors in the vector space V, then this subset is called a basis of the vector space V. For example, that this set of vectors, this e1 into n, these are this set of vectors will form a basis of Fn in general. And there are many examples, we shall look after this later. Now, using this definition and the corollary that I have written down in the at the beginning of my lecture, so we shall see that let V be a finite dimensional vector space V be a finite dimensional vector space, and since it is finite dimensional, so you must have a finite set of vectors which spans V, right? So let V1, V2, Vn, this set of vectors span V. And the conclusion is that then there exists a subset of V1, V2, Vn will form, there exists a subset of this set V1, V2, Vn, so forms a basis of V. That is, amongst these vectors, you will see that some vectors from that set will form a basis of V. And how to get this basis out of these vectors. The process is very simple, but we need to look at this very minutely. That so firstly let uh, okay, let S be equals to V1 V2 Vn. Yes, so S with a set of vectors V1 V2 Vn which spans V. Yeah, so uh, this has been given in the statement. Now if now we may see that this S maybe it will be a linearly independent set, that this S may be a linearly independent set of vectors which spans V. And if it is so, then there is nothing to prove, since this will be the this will be a basis of this vector space, right? So if the first case is if S is linearly independent, then S will form a basis, will form a basis of V. So we don't need to go further. But if not, if it is not linearly independent, then so if not, then you can find out a vector Vk belongs to the set S, this set, such that Vk is a linear combination of the preceding vectors. And this theorem has been proved in my previous lectures. So Vk can be expressed as a linear combination of preceding vectors. That is, the vectors comes before Vk. So Vk can be expressed as, so it will be beta 1 V1, beta 2 V2 plus beta k minus 1 Vk minus 1, where beta 1, beta 2, beta k minus 1 are all scalars. Okay. Now, as in the statement, it is given that uh, that V is generated by capital S. That is, capital S spans V, which has been given. So, for any vector in the vector space V can be expressed as a linear combination of the vectors of S, that is, linear combination of V1, V2, Vn. Any vector can be expressed as a linear combination of V1, V2, Vn. So, so if V belongs to capital V, then V can be written as alpha 1 V1, alpha 2 V2, alpha n Vn. Now, amongst these vectors, if you look at the kth term, then you just put the linear combination of Vk in the kth place of this expression. Then what you shall get? Alpha 1 V1, alpha 2 V2, alpha k minus 1 Vk minus 1 plus alpha k Vk plus alpha n Vn. That is alpha 1 V1, alpha 2 V2, alpha k minus 1 Vk minus 1 plus, now in place of Vk you just substitute the linear combination of Vk. Okay, so that means it is alpha k minus 1 uh, So it is beta 1 v1, beta 2 v2, beta k minus 1 vk minus 1 plus alpha k vk, sorry, alpha k plus 1 vk plus 1 alpha n vn. Then by doing easy calculation, it will be alpha 1 plus alpha k minus 1 beta 1 v1, alpha 2 plus alpha k minus 1 beta 2 v2, and alpha k minus 1 plus alpha k minus 1 beta k minus 1 vk minus 1 plus alpha k plus 1 vk plus 1 and so on alpha n vn. So you see that in this expression the kth term is missing. So you see that this vector v is actually a linear combination of v1, v2, vk minus 1, vk plus 1, vn. So that means v, the vector space v, can be generated by the set S1. S1 consists of the vectors v1, v2, vk minus 1, vk plus 1, vn. Okay, so this can be generated by this set of vectors where vk is missing. Now if S1 is linearly independent, then we are done, because S1 spans V and S1 is linearly independent. So it satisfies the axioms of a basis, right? So S1 will be a basis for the vector space V. And again, if not, if S1 is not linearly independent, then again you can find out another vector from S1 which will be the linear combination of its preceding ones, in the same way as we have seen for Vk. So if we continue this process, then eventually we get a sequence of sets Sn, such that S1 contains, firstly S contains S1, S1 contains S2, contains S3, contains Sn, and so on, where each Si has the property that it generates the vector space V. So this is the property. These the terms of the sequence has, that is the set of vectors. But since we have assumed that V is finite dimensional, so this process must terminate, because at each time we are deleting one vector like Vk. So at each time we are deleting one vector from the set of vector that we have considered in the statement. So at each time we are deleting one vector from the set. So this deletion must terminate because V is finite dimensional. And maybe at the last stage we shall get a singleton set which is a non-zero, which contains a non-zero vector. And for that reason, you can say that this singleton set must be linearly independent and it will generate the vector space B. Okay. So since this vector space is finite dimensional, this process of deletion Vk must terminate. That is, we shall arrive at a linearly independent subset of S which spans B. That means, since this is finite dimensional, so there exists some M such that Sm is a subset of S and Sm is linearly independent which spans the vector space B. That is, Sm will form a basis, of the vector space V. So thus, for any finite dimensional vector space, you can always construct a basis of the vector space V. And for example, as we have already illuminated an example, that Fn, so that Fn is, since it is finite dimensional, so it must have a basis, and the basis has been the set of vectors u1, e2, en. Similarly, for example, if you consider fx, this, the polynomial ring of polynomials over the field f. Okay, then the set, so in this, the set 1x, x square, x to the power n, and so on will be a basis of the vector space fx. Although it is not uh, finite dimensional, because this set of vectors are not a finite set of vectors. This is an infinite set of vectors which constitutes a basis for the vector space fx. Okay. So this example in turn says that the vector spaces which are not finite dimensional can also have a basis. Okay. So the next result establishes the most significant property of a basis, which is the theorem. Suppose V be a vector space over a field F. So a subset curly B of V is a basis of V if and only. So a subset curly B of V is a basis of V if and only if every element in V has a unique expression, a unique representation. Every element in the vector space B has a unique representation as a linear combination of the members of the set of vectors curly B. So a subset curly B of a vector space B is a basis for the vector space B if and only every element in the vector space has a unique representation as a linear combination of the members of the vectors lying at curly B. So why it is true? Because the proof says that, so let curly B be a basis of B. Okay. Yeah. And let and let uh, curly B equal to the set of vectors v1, v2, vn. v1, v2, vn. Okay. Then for any vector v belongs to the vector space V, suppose it has two representations. Two representations. Suppose one is summation alpha k vk k equal to 1 to n, and another one is beta k vk k equal to 1 to n. Then we have summation alpha k minus beta k vk equal to 0. Now since curly B is linearly independent, so this implies alpha k minus beta k equal to 0 for all k. So any vector v can be expressed uniquely in terms of the vectors in curly B. Okay. Conversely, suppose that every element of the vector space V, every vector in the vector space V has a unique representation of linear combination of vectors taken from the set curly B. So we need to show that curly B generates the vector space V. So conversely, let every element in V has a unique representation, has a unique representation in terms of the linear combinations of vectors taken from G, sorry, taken from curly B. Yeah. And this shows that, curly B generates the vector space. So this shows that curly B generates the vector space V. Now, so it remains to show that this set of vectors are linearly independent. Why? Suppose you consider a linear combination alpha 1 v1, alpha 2 v2, alpha n vn, and this is theta. This is theta. Then this theta can also be written as 0 v1, 0 v2, 0 vn. Now using the uniqueness of representation of vectors in the vector space V, you can imply that these scalars alpha 1, alpha 2, alpha n, these are all 0 because alpha 1 corresponds to 0, alpha 2 corresponds to 0, alpha n corresponds to 0. That is alpha 1, alpha 2, alpha n, these are all equal and it equals to 0. And this proves that curly B is linearly independent and hence curly B forms a basis of the vector space V.